Real and apparent expansions. Real and apparent expansions. We know that liquid is having two expansions, one is real expansion and the other one is apparent expansion. We cannot directly heat the liquid, we have to take it into a container. We have to take the liquid into a container. When the container is heated, both the liquid and the container will expand. Both the container and the liquid will expand. But the expansion of the container is very small compared to the expansion of the liquid. Compared to the expansion of the liquid, the expansion of the container is small. Sometimes we neglect the expansion of the container. Then the expansion is taken as apparent expansion. The expansion is taken as apparent expansion if we ignore the expansion of the container. By considering the expansion of the container, if we calculate the increase in the liquid, increase in volume of the liquid, that is known as real expansion. So, real expansion will be slightly greater than the apparent expansion. The real expansion will be slightly greater than the apparent expansion. So, we define two coefficients. For a liquid. One is coefficient of real expansion gamma r, coefficient of real expansion gamma r, and coefficient of apparent expansion gamma a. Coefficient of apparent expansion gamma a. Definition of apparent expansion, coefficient of apparent expansion gamma a. The relation for gamma a is given as V2 minus V1 divided by V1 into T2 minus T1. Gamma a is equal to V2 minus V1 divided by V1 into T2 minus T1, where V1 is volume at temperature T1, V2 is volume at temperature T2. So, gamma a is defined as the increase in apparent volume. V2 minus V1 is the increase in apparent volume. The increase in apparent volume per unit volume per degree centigrade rise in temperature. The increase in apparent volume per unit volume per degree centigrade rise in temperature. Like this, we define coefficient of apparent expansion of a liquid. Real expansion, coefficient of real expansion. The relation for coefficient of real expansion is given as gamma r is equal to V2 minus V1 divided by V1 into T2 minus T1. V2 minus V1 by V1 into T2 minus T1, where V1 is volume at T1 and V2 is volume at T2. Gamma r is defined as the increase in real volume. Here V2 minus V1 represents the increase in real volume. Hence, the definition is the increase in real volume per unit volume per degree centigrade rise in temperature. The increase in real volume per unit volume per degree centigrade rise in temperature. Expansions of liquids. The two expansions, real and apparent expansions, can be understood with the following experiment, hypothetical experiment. Let us take a liquid into a container, a spherical container with a narrow neck, long narrow neck. Suppose this is filled up to the level A. The bottle is filled up to the level A, and this is the volume, original volume of the liquid. Let us heat it. When we heat this container, we notice that the liquid level rises. So, we observe the increase in volume from A to C, the increase in level from A to C. This is apparent increase. A to C is apparent increase. But if we imagine that the container alone takes heat but not the liquid, the container alone takes the heat but not the liquid, then initially the level falls. Suppose if the level falls up to B, then from A to B, that volume is the increase in volume of the container. After the entire container expands, then if the liquid takes heat energy and thereby its volume increases, then we notice the increase from B to C. So, the increase in volume from B to C is real expansion and A to C is apparent expansion. Like this, we can understand the real increase in volume of the liquid and the apparent increase in volume of the liquid. Calculating the increase in volume of the liquid. Let us suppose the area of cross section of the narrow neck is small a, the area of cross section of this narrow neck is small a, and the narrow neck is uniform. The whole of this narrow neck is uniform. Then the relation between the expansions is given by BC into A is equal to AB into A plus AC into A. BC into A is equal to AB into A plus AC into A, where BC into A is the real increase in volume of the liquid, BC into A is the real increase in volume of the liquid, AB into A is the increase in volume of the container, AB into A is the increase in volume of the container, and AC into A is apparent increase in volume of the liquid, apparent increase in volume of the liquid. Like this we can calculate the increase in volume of the liquid. The relation between the coefficients, the relations between the coefficients. To obtain the relation between the coefficients, let us assume the initial volume is capital V and gamma g represents the coefficient of cubical expansion of the container, that is glass. G represents glass. So, gamma g is coefficient of cubical expansion of the container glass. Gamma r is coefficient of real expansion of the liquid. Gamma a coefficient of apparent expansion of the liquid. Gamma r coefficient of real expansion, gamma a apparent expansion. Then AB into A is increase in volume of the container. So, it is given by capital V into gamma g into theta, capital V into gamma g into theta. BC into A, the real increase in volume of the liquid, it is equal to capital V into gamma r into theta, capital V into gamma r into theta. The increase in apparent increase, the apparent increase in volume is AC into A, which is equal to capital V into gamma A into theta, capital V into gamma A into theta. We have the relation between the expansions as BC into A is equal to AB into A plus AC into A. The relation between the expansions is BC into A is equal to AB into A plus AC into A. By substituting the values of BC into A, AB into A and AC into A, we can cancel V and theta. We can cancel V and theta since they contain in all the terms. Hence, we will be left with gamma r is equal to gamma A plus gamma g. We will be left with the relation gamma r is equal to gamma A plus gamma g. That means, coefficient of real expansion of the liquid is equal to coefficient of real expansion of the liquid is equal to coefficient of apparent expansion of the liquid, coefficient of apparent expansion of the liquid plus coefficient of cubical expansion of the container, coefficient of cubical expansion of the container. Let us take an example. Suppose if we take mercury and it is heated in a glass vessel, then let us find its real expansion and apparent expansion. We notice that the coefficient of real expansion of the mercury is 180 into 10 to the power of minus 6 per degree centigrade, 180 into 10 to the power of minus 6 per degree centigrade. Coefficient of cubical expansion of the container, this will be obtained from the coefficient of linear expansion. The coefficient of linear expansion alpha g is 9 into 10 to the power of minus 6 per degree centigrade. This is linear expansion. So, cubical expansion will be 3 times of this. Hence, gamma g is equal to 27 into 10 to the power of minus 6 per degree centigrade, 27 into 10 to the power of minus 6 per degree centigrade. So, we will get coefficient of apparent expansion as, so we get coefficient of apparent expansion as 153 into 10 to the power of minus 6 per degree centigrade, 153 into 10 to the power of minus 6 per degree centigrade. Instead of glass vessel, if you take a copper vessel, then its coefficient of linear expansion is 18 into 10 to the power of minus 6, 18 into 10 to the power of minus 6. So, cubical expansion will be 54 into 10 to the power of minus 6, and using this value, if you calculate the apparent expansion, you will get it as 126 into 10 to the power of minus 6, 126 into 10 to the power of minus 6 per degree centigrade. That means, the coefficient of real expansion is constant, but the coefficient of apparent expansion depends on the container. Variation of density with temperature. Variation of density with temperature. Suppose the volume of a substance is V and its mass is m. Let us take a body of mass m and volume V. Its density rho is equal to m by V. Its density rho is equal to m by V. Suppose at temperature T1 degree centigrade, its volume is V1, and at T2 degree centigrade, its volume is V2. At T1 degree centigrade, volume is V1. At T2 degree centigrade, volume is V2. Then rho 1 is equal to m by V1, rho 2 is equal to m by V2. Because with the increase in temperature, there will be change in volume, but not in mass. The mass remains constant, but the volume increases by heating. Hence, rho 1 is equal to m by V1 and rho 2 is equal to m by V2, or V1 is equal to m by rho 1 and V2 is equal to m by rho 2. These are the relations, densities at different temperatures. We have the relation gamma r is equal to V2 minus V1 by V1 into T2 minus T1. Gamma r is equal to V2 minus V1 by V1 into T2 minus T1. But V2 is m by rho 2, V2 is m by rho 2, V1 is m by rho 1. Hence, gamma r is equal to m by rho 2 minus m by rho 1, m by rho 2 minus m by rho 1 whole divided by m by rho 1 into T2 minus T1. V1 is m by rho 1. Hence, m by rho 1 into T2 minus T1. Here, m gets cancelled. Small m gets cancelled, and by rearranging this relation we will get gamma r is equal to rho 1 minus rho 2 divided by rho 2 into T2 minus T1. Gamma r is equal to rho 1 minus rho 2 divided by rho 2 into T2 minus T1, or gamma r into rho 2 into T2 minus T1 is equal to gamma r into rho 2 into T2 minus T1 is equal to rho 1 minus rho 2. Rho 1 minus rho 2, or rho 2 plus gamma r into rho 2 into T2 minus T1 is equal to rho 1. Rho 2 plus gamma r into rho 2 into T2 minus T1 is equal to rho 1. Therefore, rho 2 is equal to rho 1 divided by 1 plus gamma r into T2 minus T1. Rho 1 divided by 1 plus gamma r into T2 minus T1. Gamma r into rho 2 into T2 minus T1 is equal to rho 1 minus rho 2. At 0 degree centigrade, if you take the density as rho 0, and at T degree centigrade, if you take the density as rho T. At T degree centigrade, rho T, at 0 degree centigrade, rho 0. Then substituting these values for rho 1 and rho 2, we will get gamma r into rho 1 into T, gamma r into rho 1 into T, where T represents the increase in temperature T2 minus T1 is equal to rho 0 minus rho T, rho 0 minus rho T, or rho T into 1 plus gamma r into T is equal to rho T into 1 plus gamma r into T is equal to rho 0, rho 0. Therefore, rho T is equal to rho 0 divided by 1 plus gamma r T 0, 1 plus gamma r T 0.